And sharing screen. All right. So, like always, recap of where we are. The grade ones we didn't get to yet. So, what is the difference between accuracy and precision? Zoe.
Accuracy is like how close your results are to the true result, and then precision is how close they are to each other. We do multiple trials, how close your results are to the other results.
Very good. So, yes. So to repeat what Zoe said, accuracy is how close your result is to the true value, how accurate it is. And we usually assess that by percent relative error. And we said last time, anything less than 10%, percent relative error less than 10% is considered good. Anything less than 5% is considered excellent. And for precision, we would like to evaluate it with coefficient of variation, more so than standard deviation, just because we want to correct for the size of the mean. So you want to remember that a coefficient of variation is a better indication of precision than standard deviation. And that's also a percentage. So anything less than 5% is excellent, less than 10 is acceptable. And above that, okay, redo your method or redo your analysis. So what's the difference between threshold and sensitivity? Abi?
Yeah.
Yeah. Yeah, you're soft-spoken. I think I heard you correctly. Yes, so the sensitivity of the instrument is basically the smallest change in concentration or difference in concentration the assay can detect. Okay, so the smaller that difference or that change in concentration between samples or difference in concentration between samples, that the more sensitive the instrument is. So the more it can detect it and differentiate it from instrument noise, then the more sensitive it is. Threshold, also kind of called limit of detection sometimes, and how low can you go basically in your lowest concentration that would be able to be determined by a method. So for example, when we start talking about chromatography, of course, there's always a kind of I would call it a professional fight between me and Gary, because he loves GC, I like HPLC. But I always admit that that GC has better threshold and methods and sensitivity, way better than HPLC. Don't tell Gary I said that, but it's true. In one case, CV is better measure of precision than SD. I kind of answered that, and that would be when you have compound or measurements that differ in their size. So different means. One, the mean is in the 90s, like the example I gave you last time, versus a mean in the 10s. So we need to correct for differences in the size of the mean in order to evaluate the variability or the precision of our method. Okay. Any questions? Okay. Why aren't you responding? Okay, there we go. Okay, so sources of errors, there are plenty, and students are really creative in finding new ways to make mistakes. It's just amazing, the things we learn. But we usually categorize them in 3 categories, but you will discover new categories that you will come across. But in general, we call something systematic error when you're always getting the same type of difference or error or result, but it's wrong. But every time you do it, you get that consistent wrong answer. So why? It has to do mostly with what you're using. If you're using a pipette that was not calibrated, we said last time you're trying to dispense 1 ml but you're constantly dispensing 0.8 ml because it's off calibration. It's not calibrated right. So your technique is right. You are dispensing the way you should dispense, but you're getting 0.8 instead of 1. So that's systematic error. Another example is your balance. So if again, balances need to be calibrated. pH meters need to be calibrated. Spectrophotometers need to be calibrated. So when you're working with any tool or instrument that is not calibrated, it's going to consistently give you the same error. So we call it systematic error. Random error, that could be anything. And that's the creative category for you guys. So random error, sometimes we always in lab, we remind students, if you weighed your crucible on a particular balance, write down the number of that balance. And tomorrow when you come back, like you were doing ashing, you weighed your sample in that crucible, and next day you want to come back, determine the amount of ash after putting it in the muffle furnace. You have to go back to that same balance because there are different balances, they have different errors, they have different sensitivity. So you want to go back to the same balance. If you use a different balance, you are associating or you're introducing an error in the results. So, but random error is a huge category, and sometimes there are differences between person X and person Y running the assay, because everybody has their own little technique that differ from another person. So there's always this random error. We call it experimental error. So this category is huge and can contain a lot of different types of errors. Blunders, this is a unique category because you did a major mess up in this case. You're titrating and a student tells me, I'm titrating and I used all of the volume in my burette I have and no color change. First question I use, what do you have in your burette? Are you titrating acid with an acid? Or are you titrating, you have the base in your burette? So that is a big blunder, is using the wrong reagent. Or dilution. So instead of preparing a reagent that's supposed to be 0.1 normal, they prepare the reagent different by 1 decimal point, 0.01 normal. Yeah, it's going to take like 3 or 5 burette volumes to get to your final titration if you are using a much diluted volume or much diluted reagent. So this is an example of a blunder, a big mess up, a big screw up. Why is this important now that you know? For example, next week, you will have one of the lab report questions is what types of errors you encountered? And it's not only next week, I would ask that in multiple other labs. What types of errors? So you want to categorize, oh, we did the blunder and that was what we did. There was a random error and you state what it was, or use an uncalibrated pipette or balance or whatever. So you categorize your errors. Okay. The following implies sensitivity. We just talked about that. So is sensitivity detection of only one constituent? Is it? No, that would be specificity. Has a very low threshold? No, threshold is threshold, limit of detection. Detection of minor change in constituent? Yes. So how small of a change our method can detect? Okay, so you will be plotting a lot of standard curves in the caffeine lab with the use of HPLC, in the atomic absorption lab for calcium and iron detection, in the glucose carbohydrate lab for glucose detection. So you'll be doing a lot of that, and you'll be using Excel to do that. So I'm sure you're familiar with standard curve. It's just a refresher again, and we do plot them because we're usually after determining the concentration. So this is why we are going to utilize them in food analysis, is plot standard curves so that we can determine the concentration in an unknown sample. But in order to have these standard curves, we need to figure out an identity and measurement that can be correlated to a concentration, where I can have a linear correlation. We like linear correlations because these are the easiest. Now, are they the only correlations? No. But in food analysis, a lot of the analyses, we rely on linear regression. So, and we need to have this proportionality where our concentration is dependent or proportional to a specific measurement. The measurement can be an absorption. The measurement could be a chromatography peak, area under the peak. So we would have to know what the measurement is and make sure it correlates nicely or linearly with the change in concentration. So we work with the standard curves using linear regression to construct the standard curve. And in linear regression, we have what is known as independent variable. And in many cases, the independent variable is the concentration. So we plot the concentration on the x-axis. And our dependent variable would be the y, which is dependent on the concentration. So we see an increase in the area under the curve in a GC or HPLC with higher concentration. We see an increase in absorption or fluorescence when we increase concentration. So the dependent variable is absorption, fluorescence, area under the curve. Whatever it is, that would be dependent on the concentration. And then we want to determine the correlation coefficient. We'd like it to be as close to 1 as possible. This would indicate how good the data conforms to a straight line. That means how linear our correlation is. And then the important measurement that is relevant to us is coefficient of determination, which is R squared. And why it's important to us because it tells us how good how predictive is our equation of the line. So if the closer you have it to 1, the better is the predictive power of your equation of the line, which is equation of the line in the linear regression is what? Y equal AX plus B. Y is your dependent variable, A is your slope, X is your independent variable, and B is your intercept. So that is your equation of the line. You are going to be producing that for a lot of calibration curves in the lab. Here's one example, is a calibration curve for bovine serum albumin using an assay, a bisynchronic assay, which is BCA. We usually have our new undergrad researchers practice their skills by running this assay and seeing how well they get their R squared to be. And then there will be a competition. I got 0.999, beat that. So anyway, so here's your x-axis where we prepare standards. So usually you order standard, the more pure the standard, the better it is. And we prepare different concentrations of the bovine serum albumin. We prepare the concentration based on the sensitivity and the threshold of the assay. So in micrograms per mil, in nanograms per mil, in milligrams per mil, it really depends on how sensitive and how, what is the threshold of your assay. So you prepare your standards and then you measure absorption after you add reagents to generate color. Then you would measure absorption at particular wavelengths. We'll learn all about that in spectroscopy section. And then once you have your absorbance for every concentration, you plot absorbance against concentration, and in Excel, it makes it very easy for you. You can say include the equation of the line, it will spit it out for you, include R squared, it will give it to you, and then you'll say, okay, I have really this equation would be good prediction equation. Then you would run your unknown, you get a Y value for your unknown, you plot it here, and then you calculate for X, and you get your concentration. Okay, any questions there? Okay, So significant figures. So there are rules for significant figures, but sometimes I tell you, okay, screw it. We're just not going to follow the rules in this case because it's too complicated. But we try to teach you the right way of following the rules and doing our best to get to a number that makes sense. When you report it in a table, it doesn't have 10 significant figures. You just limit it to the number of significant figures that are related to the accuracy and precision of the tools that you are using. And then I will give you some examples. I have numbers here that I will start with my little sheet here. Okay. So say you have this number, 64.72. How many significant figures I have? 4. Perfect. So I have this number. How many significant figures I have? 1. If I put this, so how many significant figures I have? 4. Okay. So if I have this number, how many significant figures I have? 1. Perfect. You just did that from high school. Great. So yes, 1. And if I have how many significant figures? 3. Great. So the 0 in between counts when you have a number here. When you don't have a number, then these won't count. When you put a decimal point and a 0, then these zeros will count. If you don't want to write a lot of numbers, but you want to make sure that you have all of your significant numbers, then you do this, and it's 4 significant numbers, and you have it in this scientific number. Okay, so that's great. Now this is easy, but how do we apply this? Well, there is multiplication rule, and there is a multiplication division rule, and then there is a summation subtraction rule, and you have decimal points, and things can get really complicated. So let's say you're doing some math that requires multiplication, and you have these values, 36.54 multiplied by 238 multiplied by 1.1. So if you look at that, you remember looking at these 3 different numbers. Do you remember from your previous math, when your final answer, how many significant numbers should your final answer have? So here, the final answer for that is 9566172. Okay, no, if you put that in the table for me, I'm just going to say no. So what would you, yes?
Isn't that supposed to be 2?
2, because you go with the lowest significant figure when you are doing multiplication or division. So then you round. So this will be 9600. So you round. Okay, so if you have addition, okay, if you have 7.45 plus 8.725 plus, that's it. Okay, so the answer here is 16.175. What should I round this to? Michael?
16.2.
You're short for 1 because you rounded to the lowest decimal points. So you go 16.18. So here you have 3 decimal points, here you have 2 decimal points. In addition or subtraction, you round to the smallest decimal point. And then you end up with 4 significant figures in this case. Okay, so let's give you something that would be relevant for the HPLC lab, where you are diluting. So you have a beverage and you need to dilute it 50 times so that the concentration fits your standard curve. Because you need to make sure you're in the linear region of your standard curve. You cannot have a highly concentrated sample above your calibration curve, then that won't be accurate for determination. So you found out that, okay, your beverage has to be diluted 50 times. You will have in lab in a couple of weeks from today, different beverages to dilute. And then when you want to calculate the final concentration in your beverage, you have to take into account the dilution factor. So you said, okay, I diluted 50 times. The HPLC program gave me a concentration based on the standard curve, a concentration of 43.5 micrograms per ml. That is something that the HPLC gave you after, solving for the X using the equation of the line of the calibration. All right, but this is in the diluted sample after you dilute it 50 times. So you need to figure out how much you have in the original sample. So I said, well, I diluted 50 times, so I'm just going to convert this times 50. So now I'm going to get a number that is 2175. And I said in multiplication, I have to go with the lowest significant figures. 50 has one significant figure. So I'm just going to say, okay, then it's going to be 2000 micrograms per mole. I don't like that. Why don't I like that? What did I do by simply removing all of these other values? I am taking away from the sensitivity of the method. So I'm just saying, okay, it's 2000, but in fact, it is 2175 micrograms. So what did I use to dilute my sample? I used a volumetric flask. So my volumetric flask, 50 ml volumetric flask, I took 1 ml from my beverage and made up the volume with 49 milliliters of water. And I use that volumetric flask. I look at my volumetric flask, it's accurate or precise and accurate to 0.05 milliliters. This number could be rounded. So I'm going to say I am, when I say 50, then it's 50.0. I'm confident to a 50.0 ml. This is rounded, it doesn't count. I'm confident to this value. So now I have all of a sudden, if I put this here, I have 3. So then this value becomes 2180. I enhance the sensitivity of my method by using the correct decimal points or significant value of my dilution based on the tool I use, which is the volumetric flask. So I really need to know the accuracy of my volumetric flask. Next week in lab, you will know that also there is specific accuracy for the volumetric pipette, for the graduated pipette, and for the mechanical pipette, and for the burette. So you will need to know these so that you can determine your significant numbers. So, like I said, there are rules, but sometimes you have a lot of divisions, multiplication, addition. We end up saying, okay, just report 3 significant figures and we'll be happy with that, because it's going to be just, too much to figure out. So we simplify it for you. Every lab, we tell you, okay, first lab, I'd like you to figure it out next week, just to practice and figure out the rules. And then from there on, we try to give you pointers in terms of significant figures. So the last thing I want to talk about is rejection of a data point. You might want to do that throughout the semester because you will be sharing data with each other. You will have several replications, and sometimes you're going to have a really off replication that is going to skew your data, gets you poor accuracy and pure precision. So in order to try to see if you can improve your precision and accuracy, you can actually statistically do that by calculating a Q value. So the Q value basically is when you see that you might have an outlier. So you would go, okay, you have 4 data points. You have this one outlier within the 4. You take the difference between your outlier and the next closest number to it. Any of your data points, the closest to your outlier, you just take the difference here between your outlier and the number closest to it. And then you divide it by your range of the data, which is maximum minus the minimum number. And you get what we call a calculated Q value. Then there is a table in your book on page 57 for tabulated Q values. So the table looks like that. It has 2 columns. It has a number of observations, so how many replications. And then it has the Q of rejection at 90% confidence. Okay, so let's say you had 3 observations or 3 replications. Your Q value would be 0.94. If you have 4 replications, your Q value is 0.76. So if your calculated is greater than the tabulated, then you reject that data point. You take it out from your calculations. Okay. So next week's lab, what you will be doing, it's a bunch of measurements with just water. So many of you might already know how to utilize different tools, pipettes, burettes, mechanical pipettes. Some of you, this is new or you've used it before and forgotten it. So it's just to get you familiar with different tools we use, and then familiarize yourself with the use of analytical balances and volumetric glassware in general. Then you're going to take several measurements and you're going to get some of these statistical measurements to determine accuracy and precision. So it's just a bunch of repetitive steps, but it will guide you through a lot of calculations. The video for the lab is already posted. The pre-lab quiz is already posted on Canvas. So the video that we have is shorter than what we shared last year with the student. We will be covering some information in the lab. Last year, we kind of tried to eliminate as much talk in the lab as possible so people can come and go quickly. But what we kept this year is very important demonstration of what you're going to see and what you're going to do. So it's very helpful to watch the video and take notes in your lab notebook of what you have observed, notes that will help you during the lab. You need your lab manual again next week. So we're going to follow chapter 6 in the lab manual. Good to just review the material we covered in class, in chapter 4 in your textbook, or recorded lecture, whatever you're comfortable with. I would like you to read the lab safety and sources of error document in the folder that's called Lab Information and Guide under modules, the top of the page. So you'll have that, and you complete your pre-lab quiz. You need your laptops. We're going to do calculations in lab. We're going to walk around, making sure that everybody's doing the calculation correctly. So bring your laptops with you, calculators as well. And the first lab, that we are having next week in ABLMS 135. Okay, so last week we had it in the computer lab. This is the first time we're going to have in our teaching laboratory, ABLMS 135. Please come on time, few minutes before time to get you settled. That would be great. The actual lab start time is 9:35. If you're there by 9:30, we appreciate it. Okay. We're going to move on to our last introductory chapter before we start going into the meat of this class. Let's see. I didn't hear you well.
Computer, your screensaver.
The image? Oh, that's my daughter's drawing.
Yeah, and then you and the white dress.
Yes, she don't yes, in the white dress. All right. Drew likes to learn about me. My name, my
You
dress.
see it for a half second, right? That was the whole time. I got to like actually even look at it, the drawing. I have to collect
No, you're welcome to ask questions.
it. I don't have a compass.
That's fine, you can ask, but you don't get +2 for these kind of questions.
I never, it's just for me. It's just for me.
I know, I'm just kidding with you. You take jokes well, so I joke with you. Okay. Not everybody can take jokes well. So.
My brain drawing for you.
What do you want to draw for me?
My brain drawing, we use paste on the whiteboard every day.
If it's good. Okay, so like I said, this is the last introductory type of chapter. It might not sound very exciting to you. You might feel a little bored, but hey, it's very important for any analysis is to learn how we prepare our samples and how much samples we take or we need to take to have a representative sample to make a decision. So this is really important, whether you're doing an undergraduate research or you're doing a graduate research or you're working in a company and you have to make decisions. So although it's not exciting information, it's very important information. Okay, to determine food quality and acceptance. That means, are you going to accept a lot? Determine that this is safe, this is good quality, it's good to go out to consumers. What is essential to do? Take your time, read. Okay, Abby, go. Huh? You think E is correct, so B and C. So there is, not in all cases, there are some cases where you can take into account the entire lot, but in many cases, you cannot just take tons of samples and analyze them all. You have to take representative of the sample. So we'll talk more into detail. How do we evaluate samples? How do we determine how many samples we take out? And in what cases we have to consider the consumer risk versus the vendor risk? And we'll differentiate between a consumer risk and a vendor risk. Of course, the consumer risk has to do with safety of the consumer. The vendor risk has to do with money. Okay. So for sample preparation prior to analysis, the following is true. For all types of analyses, particle size should be reduced to 20 mesh size. First of all, what is a 1 mesh size mean to you? Or what is a mesh? What does a mesh mean? Drew. Yes. So when we say 20 mesh, what does that mean to you? Okay, it's good to know. Yes, kind of.
20 holes per
20 holes per 1 linear inch. You're very close. So 20 openings per 1 linear inch of your whatever set you're using, mesh, whatever it's called that you're using. And this is kind of a measurement. When you mill a sample, they tell you, okay, to what mesh size you milled your sample. So that's an indication of the particle size. So that is, okay, so for all types of analysis, particle size should be reduced to 20 mesh. Enzyme activity should be eliminated or controlled. Lipid oxidation should be prevented. Wild guess. I don't expect you to know. I just want to see what Michael thinks.
Who's going with H? You,
None of the above?
none.
Okay, I'm just kidding. All right, great.
I think it's B and C.
B and C. What are you going to say? Hold that thought. What do you want to say, Shri? B and C? Alisa? All of the above? Okay, Drew.
E, B, and C.
Okay, it's B and C. So sometimes a lot of analysis we do 20 mesh is okay. Protein analysis, moisture analysis, it's okay. But some analysis that require extraction, like for example, lipid analysis that requires us to extract lipid using solvents, the recommended mesh size is 40. The bigger the number, that means the smaller the openings in that 1 inch. So that means smaller particle. So when we're extracting, we want more surface area. So basically you want smaller particle size. Okay, so no for A, you don't want any enzymatic reaction because, you know, if you're determining a certain, okay, lipid oxidation can be due to enzymatic or light autooxidation or enzymatic oxidation. So if you have lipoxygenase in there and you actually want to measure the actual state of rancidity in your sample, you want to make sure that you're preparing the sample and storing it in such a way that lipoxygenase is not continuously acting on your current sample, that you wanted to determine the current state of oxidation. So you don't want enzymatic reaction to occur because that will deviate from the actual result or the actual condition of your sample. So no enzymatic reaction. Lipid oxidation should be prevented in general. So if you have high amount of polyunsaturated fatty acids in your sample, they are going to be prone to auto-oxidation. Even if you don't have lipoxygenase, auto-oxidation is going to happen. So you want to prevent, sometimes you prepare your sample and flush with nitrogen. So you replace the oxygen headspace with nitrogen, you prevent oxidation that way. And sometimes you want to put it in a container, we call them amber bottles, so that they don't allow access of light. And sometimes for extra measure, we cover with aluminum foil. So we don't want to make sure that light is not causing any changes in the sample. So depending on the nature of the sample, we have to take extra measures sometimes so that we don't change the current state of your sample. We'll talk about that in detail. But here we go. Start a very interesting lecture. Okay, so if you have a whole lot of material that you need to determine the safety of or the quality of, is it feasible to evaluate all foods or ingredients from a particular lot? I would say no, unless it's a rapid analysis of the entire population. Let's say you're looking for metal. So the whole ingredient, flour, whatever it is, goes through metal detection. Okay, so it's non-destructive, it all goes through, you can determine presence of metal in your entire population. But in most cases, no, you're not going to take a full load of truck with grain and then analyze the entire grain. You want to do sampling. So there are different ways to do sampling. We're going to talk about that: statistical sampling, non-statistical sampling, limitations, and all of that. you want to take samples from the population that are representative samples of the population. That means when you do the analysis on these samples, you can make a decision for the entire lot. So taking these samples from the population is really important. How do you decide to select from different cans? For example, you have many, many cans, hundreds of cans. So you want to select cans. How do you do that? And how many cans you need to take to analyze? So there are ways to do that, and we're going to discuss that. So the reason we want to take a representative sample so that we can make an accurate estimation. So our decision is based on these selected samples, and based on this decision that we're making, the whole population can be accepted or rejected. So accepting a population that potentially has a component that causes safety concerns, that is something you don't want to risk. Or if you reject the population based on the wrong conclusion, and then the vendor is going to lose money because you made the wrong conclusion based on how you took samples and how many samples. So there is a cost, the impact of a cost when you reject the sample to the vendor, and then there is an impact of safety when you accept a population to the consumer. If you do anything wrong in your sampling, and which impact your decision. And that's what I meant when this is really important, might not be exciting topic, but it's really important topic to understand, to influence. Okay, so when we take our samples, the number of samples we choose would be the number of samples that is ideal to give us the least variance. Sometimes it's only enough to take 3 replications. Sometimes you need 12 replications. So the number of replications or number of samples you take and the number of times you analyze the sample, you want to reach to the lowest value of variance you can get to. So there's always this something we call sampling plan. When students were doing a project, a big component of the project was developing a sampling plan. So the sampling plan includes so many different components. It's not just how many samples and from what locations, it includes so many different things. So how many, when I say sample size, it doesn't mean weight or grams or volume. What I mean by sample size, how many samples I'm going to take from this lot. Okay, so I need to determine how many samples I need to take. Sampling procedure. Okay, am I going to use an experienced person to know where to take a sample from? Am I going to use a randomized statistical manner to select my samples? Am I going to use a mechanical sampling that takes the sample every certain time point during processing? So I need to determine my sampling procedure. Okay, sample preparation. How am I going to prepare the sample? Okay, I need to reduce the size. So I need to mill, I need to grind. What else? I need to defat, I need to remove the moisture. So what are the steps I need to take to prepare the samples? And then how am I going to store them? Am I going to store them in amber containers? Am I going to store them in under refrigeration, flushed with nitrogen? So what are the storage conditions? And transportation, if I have to take samples and then transport them to a lab, under what conditions I need to travel? Is it going to be a refrigerated truck, for example? Or what other specifications are needed during transportation? So all of these different components go under sampling plan, the whole plan. Okay, I think you guys are dropping like flies. I see people falling asleep, so I'm going to stop here because it's Friday. So happy Friday, 5 minutes early. We'll continue from here on Monday. I haven't meant to be holding this hostage. I'm trying to figure out how to get out of here.
For what?
I need to go to make sure I stop the recording. Now I don't know where my controls are. Oh, it's right there.
Oh, it's on the second. Oh, because it's the second screen. Which side does it go? And meeting for all, or do you want to check the?
Stop sharing and then stop recording.
Oh, now it's come back to this one. So there's the recording.